Alright, so last competency in CRS says express vectors in C of A as linear combinations of the columns of A that correspond to pivot columns. Now we've actually done this before. You use the RREF to identify the linearly independent columns, and then you can use those to get any vector in the column space. But let's do it again. It doesn't hurt to see another example. All right, here's an example of matrix A, and let's get rid of that. And I'm not sure why it's doing that, but let's go down a little bit. All right, so let's go ahead and row reduce this. Use your favorite row reduce software, and you'll get the following. You'll get, let's see, 1, 0, 3, 5, 0, 9, 0. And then here I have 0, 1, 2, 4, 0, 2, 0. Next one you get is 0, 0, 0, 0, 1, 8, 0, and 0, 0, 0, 0, 0, 0, 1. Now this is in REF form. You can check the pivot columns and everything. So you can identify the pivot columns here, 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 and here. So that's columns 1, 2, what column is this? 1, 2, 3, 4, 5, and 7. All right. So that means that these columns 1, 0, 2, 1. 2, column 2 is 0, 2, minus 1, 1. I got that from here. That's column 2. Then up to column 5, it's minus 1, minus 1, minus 2, 0. And last column is 6, 7, 12, 6. That these columns span C of A. Okay. So to express any vector B as a linear that's in the column space as a linear combination of these, well, let's say suppose B is in C of A. That means that B is equal to some combination of these, which I can write as x1 times the first one, 1, 0, 2, 1, plus x2 times the second one, 0, 2, minus 1, 1, and then plus x3 times the third one, plus x4 times the fourth one, which is 6, 7, 12, 6. Now we've seen this before. All this says is that B is equal to this matrix here, consisting of the columns 1, 0, 2, 1. Okay, I get tired of writing this, but I'll do it one more time. 2, minus 1, 1, minus 1, minus 1, minus 2, 0, and then 6, 7, 12, 6 times some vector x. So we can solve this by creating the augmented matrix. Let's call this matrix, I don't know, we had A for our original name, so we call this matrix B. So you just create the augmented matrix B, B, and row reduce. Now I'd like you to notice something, that if we chose for our vector B one of the non-pivot columns of the original matrix, so suppose we chose, let's see, column 3 here is a non-pivot column of the original matrix. Now suppose we did this with column 3 here, which is 3, 4, 4, 5. So suppose we had B is equal to 3, 4, 4, 5, which is column 3 of the original matrix. Then we would take the RREF of B, of big B, with little b. All right, that's just what I said here, that if I want to find this vector as a linear combination of 1, 2, 3, 4, these 4 vectors, I have to take the matrix formed by these 4 vectors, augmented by this vector, and take the RREF. Now what will this RREF be? I actually don't have to do any work at all. I go up here and look at the REF for these guys. Now the REF for the pivot columns is the identity. The REF for the vector B is going to be just this 3, 2, right? Because I can shuffle these columns around, and that's not going to change the REF of the non-pivot columns. So I could shuffle this over there and get the same answer for my REF. Okay, so that means I'm going to get here the identity matrix 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, and then I get this column here that corresponded to column 3. That would be 3 2 0 1. Okay. Again, was it 3201? I think this is 3200. Okay. Again, I just want to emphasize that I can shuffle around these non-pivot columns and still get a REF form. As long as I don't put the non-pivot column too far in advance, if I can put it back, I can put it farther back and still get the same thing. Why is that? Because if I do the row operation on the row, it doesn't really matter what order I list the components, I'm still doing the same row operation. So I could put this 3 2 at the end, and I could ignore the other non-pivot columns and end up with this result. And this is just telling me my answer. This is telling me that to get this third column, I'm going to take 3 times the first. I guess it's going to be, let's see, I guess it's going to be, how would you do this? It's going to be minus 3 times the first column plus minus 2 times the second column. Let's verify that. Did I do that right? No, it wouldn't be negative because we're augmenting. We're not solving homogeneous. We're augmenting. We're trying to get this matrix here in terms, this vector here in terms of the other one. So that's considered as a constant matrix. And you can verify that 3 times the first column plus 2 times the second column is giving you the third column here. 3 times 1 is 3. 3 times 0 plus 2 times 2 is 4. 3 times 6 plus 2 times minus 1 is 4. 3 times 1 plus 2 times 1 is 5. Okay, so that's how you can get, that's how you can understand getting these non-pivot columns in terms of pivot columns, just kind of as a reshuffled version of the usual augmented procedure that we've seen before. Okay, so this really does tie together stuff that we've seen already. Bottom line is, once you identify the pivot columns, you put them into a matrix, and if you want to get any vector as a linear combination of those vectors, you just augment and row reduce, and then you can read off the coefficients from the last column. Okay?